All right, today's the last section of the last words are hard. The last section from chapter 3, and we're going to cover inverses of functions. So, one thing that we're going to start with is the inverses of a relation and the difference between what's a relation and a function. And then we'll do inverse functions, the horizontal line test, and then lastly, just actually finding the inverse functions of a formula. Inverses are nice because basically what it does is if you think of f of x and that's your form of input, then whenever you, let's say it's maybe like we talked about previously, the price of tickets, or if you have the price this much, then you're going to sell this many tickets. Well, what if you want to know the opposite? What if you know how many tickets are sold? Then, based on like prediction models, what would be the amount of tickets that you would have to have sold? Or, sorry, what was the price you sold the tickets for? Something like that. So, this looks intimidating at first, but this is just a little bit of set notation. So, the inverse of a relation is, you read this as the set such that the ordered pair B, or the set of ordered pairs BA such that AB was in the original relation. This little funky looking E, this means contained in. So the inverse of a relation just means that you take your ordered pairs and you swap the order. If it's 1, 3, so like if I had 1, 3 was in one relation, that means that the inverse relation then that means 3, 1 will be in the inverse relation. Something simple like that. Now, what separates a relation from a function? Functions are you have one input and one output. A relation, you can have one input with multiple outputs. That's the difference. So like when we think of f of x is x squared, if I plug in 1, I still get 1. If I plug in 2, I get 4. If I plug in -2, I get +4. It's okay that different numbers map to the same thing, but you can't have the same number map to two different things. That would be like if when you changed gears in the car, then when you got it on drive, it was drive, but it was also neutral. So you don't want to have that one input with two outputs. That would not be good. So relations are usually more of just kind of like you've collected like these pairs of data, but a function is an actual mapping between an input and an output. So if we start with this first relation, A, so we need to determine the inverse of each of the following. So let's start with A. Like I said, it's really easy if you just have ordered pairs. To find the inverse relation, all you do is just swap the order. -1, 4, 2, -3, 5, 0. Because what this is saying is 4 maps to -1, -3 maps to 2, 0 maps to 5. Which means your inverse relation would be -1 maps to 4, 2 maps to -3, and 5 maps to 0. So it's just reading these ordered pairs instead of xy, you read them as yx. And that's all it takes for the inverse relation. And so if you look, so R represents all of the original points. Here's 0, 5. Here's -3, 2. And here's 4, -1. And then you can find their corresponding points. Here's -1, 4. Here's 5, 0. And there's 2, -3. And so it's kind of interesting to see the way they're almost kind of reflected in some cases. Or like kind of you picked up some of the points and then rotated it. But some of them just look like they actually were just picked up and moved a little bit more differently. So like for -1, it looks like you took a 90-degree turn going this way, because it looks like you went, if you pick this point up, and it kind of just did like that rotation. But 0, 5 went to 5, 0, so it went 90 degrees almost in the opposite direction. Now, this one's kind of easy. The inverse relation of y equals x squared is just x equals y squared. Because kind of what's going on is, like I said, if you have two inputs go to the same output, that's fine. Because if I do f of 1, that equals 1. But so does f of -1. That's okay. So this is still a function. Notice now there's an issue, though, whenever we try and deal with the second one as a function. Because, well, let's call this one g of x. Or let's call this one g. Because x is now kind of like your independent variable. What makes this true? Well, x is the input, so I can have 1, which is okay. But I can also have 1, -1, which is not okay. Because this is, to go back to, this is probably notation you haven't seen in a while, but here's 1, and here's -1. The whole point is here, 1 maps to +1, but it also maps to -1. It's like having the two things wired on the same button. You don't want the elevator button that takes you to the first floor to also be the one that takes you to the 100th floor. And you don't know which one it's going to be when you press it. So, relations are good in certain circumstances, but we want to deal with functions. And you can see here, this is kind of what I meant by sometimes it looks like you just rotate it 90 degrees. So like with this one, the original relation is here. And part of the reason you can think about it is, so if x squared equals y, that's going to imply that x should equal the square root of y, right? but you would say it equals plus or minus the square root of y. Which this kind of makes sense when you look at the way that the parabola laid on its side is. The top part looks like, let me get a good color for separating these two. The top part here, this looks like the square root of x. But down here, this now looks like the negative square root of x. So it makes sense that if it's plus or minus the square root of y, then it would make sense to kind of have those two pieces go together to make the relation. So one thing just to kind of introduce here, x squared is a function. Its inverse is not a function. Because the problem is if I tell you, okay, my output was 4, you go, that's great, but I don't know if you plugged in 2 or negative 2. And then there's some functions where it equals those points multiple times, more than just twice. So you have to be careful. We're going to have special either domain restrictions or specific functions that will have, I guess the best way to put it is nice inverses. Because yes, the square root is the inverse operation of squaring something. If I took the fourth root, that would be the inverse operation of raising something to the fourth power. But when you do this, you're not taking into account sometimes that there's a plus or minus sometimes that's introduced, or just maybe you can't actually factor those values out. And so to finish this one, we need to talk about the domain and the range. So let's talk about the original relations, domain and range. It's just x squared, right? So its domain is negative infinity to infinity, and its range is 0 to positive infinity. And this is the nice thing. This is what makes these so easy to deal with. What's our inverse's range, or domain and range? It's just swap the two. The domain of R is the range of R inverse. The range of R is the domain of R inverse, which makes sense because you're taking the inputs and making them the outputs, and the outputs and making them the inputs. So domain is input, range is output. If you do the inverse, the domains have got to switch. So the domain is now 0 to infinity, and the range is negative infinity to positive infinity, which you can even see here on the graph. There's no values you get to plug in to the left of 0, and these are going to continuously climb up and down, so that's why your range would actually be negative infinity to infinity, and the domain be 0 to infinity. But the easiest way to remember it is just because of you're swapping inputs with outputs, which means the domain and range, by definition, are swapping. And this is one of those things where mathematicians decided some kind of bad notation somewhere along the line, and it never really got, not that it didn't get fixed, but not that it got addressed either. I talked about that if you have like x to the negative n, then that equals 1 over x to the n, because the negative exponent just tells you change the position. If I had 1 over x to the negative n, that would be equal to x to the positive n. The negative just says if it's in the numerator, put it in the denominator, and if it's in the denominator, put it in the numerator. But when you write the notation as f to the negative 1, you have to know what you're talking about. Typically, you'll never see f to the negative 1 actually represent this, just because the negative 1 exponent is so vital to this. If you see f to the negative 1, that means find the inverse. It does not mean do 1 over the function. If you'll see 1 over the function, you won't see f to the negative 1 representing that. It is kind of solved a little bit in trig, because sine inverse, for example, sometimes you'll see it written as arc sine, which arc means the inverse sine of x. So with trig functions, you're given an angle and it puts out a value, which means if you do the inverse of a trig function, you're taking a value and it's telling you the angle. So think about like an arc of a circle. The arc sine makes sense because you're kind of looking at how far has that part of the circle rotated. So just be careful of this. Now the horizontal line test, this is the best way to check if you have a graph. And basically all it says is if you have a graph and you hold your pencil sideways, if you slide it up the graph and there's never a point where the pencil is touching the graph in 2 places, then congratulations, it passes the horizontal line test. The horizontal line test is a simplification of the actual property you need for a function to have an inverse. So that's kind of what the horizontal line test is doing, is graphically telling you, does this function have an inverse? And I'll explain more why the horizontal line test works after an example. Or nope, never, it's not mine. I had my slides mixed up in my head. So what the horizontal line test is doing is actually checking if it's 1-to-1. And basically a function is 1-to-1 implies that every input has exactly one output. So if you think of a function like f of x equals x cubed, this is 1-to-1. Which means f inverse exists. So, and it makes sense. If I do negative 2 cubed, I know that I'm going to get out -8, and I know there's nothing else that produces -8 in that domain. However, if I do f of x equals x squared, this is not 1-to-1. Which means f inverse of x squared does not exist. And it's very easy to show a time when a function's not 1-to-1. You just need one counter example. Because f of 2 is equal to 4, and so is f of -2. 2 does not equal -2. That's nothing groundbreaking in mathematics, but it is used in our argument. So if a function's 1-to-1, all you got to think of is one output for every input. So if you plug something in, it goes to exactly one thing, or it has only one thing that maps to it. So something like a x squared function where outside of 0, every other value has 2 x values that will map to it, those are different inputs go to the same output. What you're looking for is every input has exactly, or every output only comes from one input, versus, again, x squared is the example. Multiple inputs go to the same output. That means it's not 1-to-1, which means it will not have an inverse. So determine if the following functions have inverses. So, again, start with a counterexample. Absolute value of x. If I do the absolute value of -2, that equals 2, which is the same as the absolute value of 2. So, not 1-to-1. Therefore, not invertible. And so not invertible is just a way of saying that the function does not have an inverse. Now, we are not going to do the very rigorous mathematical proof that x plus 2 cubed is 1-to-1, because it's very easy to disprove something being 1-to-1. It's kind of a little bit harder to prove that it's 1-to-1. But that's where you can use like the horizontal line test as your argument. So A, we just used a counterexample. B, well, let's graph it and actually see. So you can see that the way this function is going on the right, it never has a place where the horizontal line crosses twice on the function. Thus, it's always going to be 1-to-1 throughout. Now, if you go, well, I can't see above the function, or I can't see the whole graph. That's very true. The thing is, you just have to make a good argument. So, and kind of just from the way that these functions behave, you are able to make certain arguments for or against them being 1-to-1 or not being 1-to-1. Now, finding the inverse function is a little bit, I don't know if I would say it's trickier, but a lot of people stumble with it. So, because this one is a little bit more algebraically intensive. So, first thing you do is you just take f of x and replace it with y. The main reason for this is just it cleans up your notation. The second thing you do is once you have it as y equals something, swap x and y. And the reason for this is because if you swap x and y, it starts to make a little bit more sense. And I'll explain why. Because then you solve the new equation for y, and then that y is now, you have y equals some new equation. That equation is the inverse. So y equals a function of x, swap x and y, solve for y again, and then replace y with f inverse. So we're going to do this with these two functions. So, first one. Step 1. We need to change this to y equals x minus 1 cubed plus 2. Step 2. Swap x and y. So now I have x equals y minus 1 cubed plus 2. Now, 3, solve for x and y. Or solve for y. Get it by itself. Now, the thing is, do not expand y minus 1 cubed. Can you do that? Yes. Do you want to do that? No. Why? Because if you do that, now you have turned this into an intense factoring problem. Don't turn it into an intense factoring problem. Make it easy on yourself. Leave stuff like cubes and square roots and third roots and weird stuff like that. Leave those be. Don't try and overexert on those things. And plus, it's easier just to take the cube root of something than factor something. Spoiler for what comes in a moment. Because first thing I need to do, I'm trying to get y by itself. That's the end goal. But I can't just take the cube root of both sides here, because if I take the cube root of this is one other thing. If I do the square root of x squared plus y squared, that does not equal the square root of x squared, or I don't even need the squareds here. If I take the square root of x plus y, that is not the same as the square root of x plus the square root of y. How can we easily demonstrate this? Let's take the square root of 5, which is equal to the square root of 4 plus 1, which does not equal the square root of 4 plus the square root of 1. Because if that were the case, we would have 2 plus 1, which equals 3. And the square root of 5 is definitely not 3, exactly. You know the square root of 9 is 3. So don't split things up like that. That's not how it's supposed to work. So you can only take the cube root, or you can only remove a cube by taking the cube root of just that piece. But the other thing is, equations are balanced. What you do to one side, you have to do to the other. So first thing we're going to do is I'm going to try and get this y minus 1 cubed entity by itself. So to do that, I'm going to subtract 2 from both sides. So once I do that, I have x minus 2 equals y minus 1 cubed. All right, now we're in business. Now I need to get rid of the cube, or the cubed part. To do that, I'm just going to take the cube root of both sides, and that's going to leave me with the cube root of x minus 2 equals y minus 1. And then I'm just going to add 1 to both sides. And that's going to get me the cube root of x minus 2 plus 1. The 1 does not go under the cube root, is equal to y. Box it in the little aside so it doesn't get confused. So then we have y equals the cube root of x minus 2 plus 1. And then the fourth and final step, we replace y with f inverse. Now, if you're worried about confusing that this plus 1 goes under there, you can, under the cube root, you can always just put it as 1 plus the cube root of x minus 2. That also works. But now we've actually solved this one out, and we now know our inverse. And I can use this to demonstrate a example. So let's say we did f of 1. Just because I want to make this easier, because I don't want to have to cube something. I mean, my word, if I get to a point where I cube 5, that's going to be 125. So let's keep the numbers small. So if I do f of 1, I get 1 minus 1 cubed plus 2, which would be 0 cubed, which is still 0, plus 2, which is just 2. Now let's do f inverse of 2. If I do f inverse of 2, I get the cube root of 2 minus 2 plus 1. So the cube root of 0 is 0 plus 1 is 1. And so from that example, you can see that our inverse seems to be working properly. If you had done, and this is a good way to test it, pick easy numbers. Like I picked 1, and then I got out 2, and then I checked and said, okay, if I plug in 2 to the inverse, do I get out 1? And I did. Now, are there times where you may just get extremely lucky to where you messed up somewhere in your algebra and still get the right answer? Yes, but it's a lot less likely. So, sorry. So instead of struggling there, just go through and do a quick check. Pick easy numbers. Heck, if you want to plug in 0 because it's easier, just plug in 0. I'm always for taking the path of least resistance, and if I can plug in 0, I will. The only reason I plugged in 1 here was I knew I was going to get to do 1 minus 1, which would, in turn, actually get me 0. So, still took the lazy route, but I took the lazy route in a smart way. So, notice the way the operations were done. I had something added to what my y was kind of trapped in, so I subtracted it over. Then I had the whole thing that y was trapped in isolated, so then I could remove the cubed part with a cube root. And then I just needed to get y by itself, so I just needed to add 1 to both sides. Not the worst thing in the world to deal with. This is the one that messes with a lot of people. And for valid reason. It's not as easy as the previous one. So y equals x minus 3 over 2x plus 1. Well, I'm just jumping ahead, aren't I? That or I can't count. So notice here, this is the issue. When I swap x, no big deal. But now what ends up happening is now I have y minus 3 over 2y plus 1. And thus with that, my problems have grown a lot more. Because now it's not just, I can't just solve and subtract and do all that. I have to deal with multiple y's. So now it's not just getting the single y by itself, it's trying to find how to put these two y's on the same side, but also making them where they can be factored out, so I can end up with y equals something. So I don't have room to write it on the left and the right, but what I'm going to do is I'm going to multiply both sides by 2y plus 1. And if I do that, I'll get x times 2y plus 1. And if I multiply 2y plus 1 to this function, then what I'm going to have is that y minus 3 is the only thing left. Because it would be like if I multiplied 2/5 by 5. The 5 in the numerator and the denominator would cancel each other out. And so that's going to be my main goal here. And so once I do this, I'm going to distribute this, and I'm going to have 2xy plus x equals y minus 3. Now your goal is going to be not necessarily get y by itself, but get everything with a y on one side, and then get everything without a y on the other side. So to do that, so everything without a y, I'm going to move to the right. So I'm going to subtract x from both sides. But at the same time, I'm also going to subtract y from both sides. The reason for that is, when I do that, those will cancel. Those cancel. And then, because I don't want to try and write down there, I now have 2xy minus y is equal to negative 3 minus x. And so here what I've got is a little bit easier to deal with, because now notice I have two terms with a y, and so if you have things added or subtracted and the same thing shows up, you can just factor it out. So now I have y times 2x minus 1 is equal to negative 3 minus x. Then we end up with y equals negative 3 minus x, and then I'm going to divide both sides by 2x minus 1. And so the inverse ends up being 2x minus 1 in the denominator and negative 3 minus x in the numerator. And so that was step 3 completed. Now lastly, we end off with step 4. And that's saying that f inverse of my brain doesn't work sometimes. F inverse of x equals negative 3 minus x divided by 2x minus 1. And so if you ever have a case where multiple y's show up, your goal isn't just going to, your goal shifts from get y by itself to get everything with y on one side and everything without a y on the other side. Because the goal will change from isolating y to factoring out y in order to isolate it. So it kind of introduces this extra intermediate step to all of your work that you're doing. And what's the thing that's special about, or one other thing that's special about inverses is if you compose a function with its inverse, regardless of order, you'll always just get back x. And that's why I was talking about in the previous lecture, where the order that you compose things is important. F of g of x versus g of f of x. Those are going to result in different functions, unless they're inverses of each other. And if they're inverses of each other, they're just going to produce the function x. Because think about what you're doing. You're taking a value, you're mapping it, and then the inverse is mapping it back. So in the end, it's just going to go right back to where it started. And it doesn't matter which way. If 3 maps to 7, but then 7 maps, and then you go backwards, so 7 maps to 3, f of f inverse of 3 is still 3. Versus, so let's just take that for example. Let's just say 3 maps to 7. So then if I do f of f inverse of 7, then f inverse is going to map to 3, because you're going to read it backwards. But then 3 is going to map right back to 7. Then do it for the opposite direction. F inverse of f of 3, make sure to nest your parentheses appropriately. F of 3 maps to 7, so f inverse of 7. But 7 maps right back to 3. So that's one of the special properties of an inverse, a function and its inverse, is the composition will always just get you back what you plugged in. So, and that's kind of a test that you can do, is you do the function composition, and if when you do your function composition without any values, you just get back x for both orders, then you know the two functions are inverses of each other. versus if you did like g of x and then you did, and that came out to be x, but then you did f of g and that came out to not be x. It's not like you call it like a half inverse or anything like that. You just say they're not inverses of each other. So that's just kind of a neat thing about those. And so that does it for chapter 3. Next thing we'll do is we'll start chapter 4, and we'll just keep going on through like we've been with 3.